So this module will help us find applications of the exponential and logarithmic functions, and all the problems will follow the same structure, whether they are in uninhibited and unlimited growth or whether they're decay. They're all going to be the same, and they're going to follow this theorem. So if you have a function y that satisfies this equation right here, then the function will be of the form c e to the kx for some c, some constant c. And that constant c is going to will be dependent on the problem itself. So as an example, I'll tell you what kind of problems you're going to find. You're going to have things that will say you have a population, you can have an amount invested in a fund. You can have several things, and they'll tell you that that function will depend on another variable, usually time. So I have it here with x, but it's usually going to be time. So let's put it as dt, and it's going to be a constant times t. Let me write any constant right now. So 0.01, how about that? So there's going to be some verbiage to it, and then they'll tell you there is an initial, and whether it's a population or an amount or something, or they'll give you a value. So I'm just going to write, for example, if here you would have the initial amount is, say, 1,000. And it could be bacteria, it could be populations of anything, it could be an amount in a fund. As I said, there are many problems, but they're all the same. They follow the same structure. The only one thing you have to notice is that k could be positive or negative. If k is positive, this is an uninhibited growth, and if k is negative, then you have decay. So that's the only thing. Well, now the types of questions that you will have are the following. Firstly, find an expression for y with respect to time, or find a model that, or an equation that describes the situation. Find a model for the described situation. The wording can change, but they're asking you to find a formula for y. And now the other thing they can ask you is y at certain values. For example, they can tell you that the model is for where an amount or a population given in months, and then they can ask you, well, what is the population after 10 months? All these kinds of questions would be translated into this. And lastly, they can ask you something like, how long will it take for the population to grow by a 10%, or how long will it take for the population to double? Not writing everything, but those are the kinds of questions that you're going to have. So let's go ahead and solve this using the theorem that we have. So for starters, let's start with finding the y as a function of t, and the theorem tells me that y as a function of t is going to be a constant times e to the k is 0.01, and then times t, the independent variable. Notice that I changed dx for a t, so I changed dx in the theorem for a t there. But the same idea. So why do I care about having an initial amount? Is because I'll use that to find the value of c. So I say y at 0, and I evaluate this is going to be c times e to the 0.01 times 0, so c times e to the 0, and that is just c, but y to the 0 has to be equal to also 1,000. That's the initial condition, so I get that c must be 1,000, and then I obtain y of t is 1,000. I'm substituting in for c, and then e to the 0.01t. So that is the answer for part A. You see, everything depends only on t. Now for part B, let me continue up here. You want to find y at 10, but now I have an expression for a y, and it would be 1,000 times e to the 0.01 times 10, which is going to give you 1105 roughly. And here you would have to write, if it's dollars, would be, if the problem is for an amount invested, then would be dollars. If the quantity that you're looking for is a population, that would be the number of bacteria or whatever population you're looking for. So, but you do want to include your units. In this case, since I'm not talking about a specific problem, I'm just going to leave it without units, but make sure to write those units. And now C would be how long for the population to double. And this is the one that is a little more complicated, so let's go ahead and try that. So what I want to find is t such that the population becomes 2,000. So since I started with 1,000, how long will it take me to double? So I'm going to have here 1,000 e to the 0.01 t equals 2,000. So I have to solve an exponential equation like the ones we did in the previous video. So divide both sides by 1,000, and you get that e to the 0.01 t would be 2,000 divided by 1,000. That's 2. And now I have it in the form that I wanted, with an exponential on one side and a number on the other. And so I have the t, or my variable I'm trying to solve for, I have it as an exponent, so I want to bring it down, and to do that I take natural log on both sides. So I get natural log of e to 0.01 t equals natural log of 2. And then I use the fact that natural log of e to the 0.01 t is just 0.01 t, because the logarithm and the exponentiation are inverse functions to each other, so I just get that, and then I divide by 0.01, which is multiplying times 100, and I obtain 69.3 approximately. And here the units will also be given to you in the problem. You'd say, whenever they describe y, they would say, oh, it's the number of bacteria, if you want. That's a typical example. The number of bacteria per second. So then here time would be given in seconds. So the unit will depend on the problem itself. But I'm doing a very general problem, so I'll leave it like that. Now, this whole module involves 2 sections, both sections in the book. Whenever you read it, or if you already read it, you'll see they separate the growth models and the decay models, but they are ultimately the same equation. It's just the sign of decay varies. So this is very simple. It's very straightforward. But if you have any questions, please go ahead and ask me, whether it's in the comments or in the conference. So that's it for the video.